So, g'day, my name's Nicholas Crouch. I work for the Maths Learning Centre at the University of Adelaide here. I'm going to try and turn on the light for this document camera. No, that one. And loop. Which one? Nope. Gee, give it a moment to adjust. Awesome. And next trick will be to zoom in. No, that doesn't do that. And maybe. Oh, hey, sweet. All right, that's the thing I want. Sorry about that. Trying to fiddle with the document camera. So, the first thing we were asked about is differential equations, and that's where I'm going to start today. So, playing with differential. What does it mean for it to be a differential equation? Is the first thing we've got to ask. So, differential equation means, if you look at these examples up the top of the page, means that it's an equation that relates the derivative of the function to a function of that to some function of that variable. All right. So we don't necessarily know the exact function, and part of what we're looking to do usually is to try and find out what that exact function is. So this is one of those things that is actually quite commonly used. We quite often know a lot about the rate of change. So you'll hear us talk about the derivative as the rate of change, and so in this case we're going from information about the rate of change of a function to the actual function itself. All right? And it is quite a complex field, and you should be aware that for your purposes, you're doing quite simple things. All right? Most of your differential equations are going to be quite simple. I'm going to point out this word in this question here. The question is the differential equation separable? So the differential equation being separable means that I can write my equation. So let's work with that one. So we've got sort of x times y dashed minus y is equal to x. And what that's saying is, for my function to be separable, basically I'm going to do dy on dx is equal to a function of x times a different function of y. All right? So we separate the variables into two different functions. And what we're going to do, the first thing we do when we see something like this, is that we separate them. We actually do sort of 1 on g of y, and dy is equal to f of x dx. Now, it's sort of almost mandatory for math lectures to stop at this point in time and go, when I split the dy and the dx, all right, the dy and dx is actually a single thing. It's the rate of change. And so we actually say it's an abusive notation to split it like this, but, you know, did a whole lot of sort of pure math stuff, and basically it says you're allowed to do that. Okay? If you really care enough about it, you can do 3 years of mathematics and go, you can do it. But if you're just going to take it on faith, you're allowed to do it. Awesome. So, can we do this with this equation? So, first thing we're going to notice is y dashed is equal to dy on dx. Those are the same, that's saying the same thing. So we can sort of, we've got it in the right form. And so what we've got is we're going to start moving this stuff around. We're going to have x, y dashed. So the form that we're looking for has the dy and dx by itself. So we're going to try and get the dy and dx by itself. X plus y. You know that thing where I'm going? I'm not seeing it. It may or may not happen, but I'm not seeing it. So y dashed is equal to x plus y on x. If I look at this, I'm going, actually, I can't see a way to write that. Because of this plus here, I can't see a way to split that into a separable differential equation. So I don't think this, I'm actually going to say that this isn't a separable differential equation. All right? I could be wrong. One of the other things we should bear in mind is when I do this stuff, when you do something on the fly as a lecturer, and sometimes you make mistakes and we're worried about trying to tell you the right things to do, not necessarily give you the right answers. So in this case, I look at it and go, I actually don't see a way to do it. So I'm going to go, not, oops, that's a bell. This is why I write everything in pencil usually. So I'm going to say my thing is not separable. Okay? Now, next part of this question, it says verify that this is a solution. This is one of our favourite tricks. We're not going to ask you to find the solution. Verify means check that it works. Okay? So we're going to check y is equal to x ln x is a of x, y dash minus y equal to x. All right. So, all we're going to do, so y dashed is equal to. So I'm going to differentiate this. We're verifying it, so what we're saying is if I differentiate it and put it in as y and both y and y dashed, the equation will be true. Okay? And we've said we've got stuff involving y over here, and we say it's going to simplify down to x. So when we verify something, I put it into one side and hope that once I've done my simplification, etc., I end up with the other side. Let's see what we do. So because this is a product of functions, we're going to do product rule. So derivative of the first term is going to be 1 times the second term plus first term times by the derivative of the second term, which is going to be 1 on x. We're going to simplify this down to say ln of x plus 1. All right? I'm going to whack brackets around the x so it's clear that I'm just doing ln of x, not ln. So sometimes that brackets around the x says that's the thing I'm doing ln of. So my equation says x times y dashed. Y dashed is this. So because we're timesing x by something which is a sum, we're going to put brackets around it to make sure we don't lose our terms anywhere. And we're going to have something like that, plus, what do you say? Oops, minus x ln x. All right. So remember, we're just starting with the left-hand side of this equation, and we're hoping it's going to simplify down to this right-hand side of the equation. We're not going to say it's equal to that at any point unless it works out to be. All right. We don't say that it is. We're hoping that the working will show that it is. So we expand out x ln x plus x minus x ln x. Well, hey, check that. X ln x cancels, and I'm left with x. So notice what I've done here is I haven't said that this thing is the I haven't made the statement that this is true. I've shown it by doing the working. All right, bit of expanding, bit of cancelling, and so I've shown. So we. Now, one of the things, if we'd read through what we were told to do in the course material stuff, they had a thing about what you do with the exams. They've actually gone to the trouble of making sure you make a statement. So see how we've made a clear statement. We have shown And we've said what we've done. We have shown that this is a solution. All right? We want to be clear about making nice, clean statements about this. All right? It's actually kind of, we should be doing that at every stage. If you're asked a question and you need to do some working, do the working, show the working. And it's really important that, that you show the working. All right? And if you don't know what to do, like if you get asked a question about a differential equation and you go, I don't know what to do, but I know it could be separable, so I'm going to check if it's separable. And that, so there are two reasons for doing that. Firstly, if you don't know what you're doing, you want to be able to say it and write something so the person who's marking it can give you some marks for something. You've got nothing on the page, that's how many marks you get. If you've got something on the page, then they can give you marks for it. The other thing you're doing is you're giving yourself an you're prompting yourself to do something, to remember what you should do. All right? If you go, I don't know what to do, but I do know it's a differential equation, so that says it could be separable or it could be something else. I'll just say that. I'll write that down. I'll tell people what I'm doing, even to the point where you say, I don't remember exactly what to do with this, but since it's a differential equation, it could be separable, I'll check. If you do that, you'll do a lot better than you think. Okay, good work. I'm actually going to do the second part of this one, because I think it's actually kind of important to do this. So, just because I want to see if this is going to work. So, this second one is talking about this equation: xy dashed minus 2y is equal to 2. So, they're asking the same question: is it separable? So what I'm going to do, I'm going to follow the same process. I'm going to go put everything bar the y dashed on one side. Okay, so I'm going to have y dashed is equal to 2y minus 2 divided by x. I know what I'm talking about. Seriously. So, may not look like it's separable at first, but I know that I could write this as 1 on x times by 2y minus 2. And so you can see clearly now I've got this as a function of x and a function of y. So we've got a separable. So this is separable. So again, we've been asked the question, is it separable? We've done a little bit of calculation, we've made that statement. And again, we've been asked to verify this is a solution. So we've got y is equal to x squared minus 1. So we're going to find y dashed is equal to 2x. So I'm going to go back to the original equation, and I'm going to go x times by y dash, which we've said is 2x, minus 2 by x squared minus 1. So we're not going to go it's equal to 2, because we're hoping that's what's going to show out when I expand this out. So x times 2x is going to get me 2x squared minus 2x squared plus 2. Hey, that cancels with that, and I'm equal to 2. So we have shown y is equal to x squared minus 1 is a okay, so going to have a bit of a scan of this thing. So that's the basic part about this, all right? There's going to be a little bit more that we're going to do, but this is the basic work, all right? Whenever we do this, so like I say, you don't do a lot of differential equations. What you see here is like what we call a first order differential equation, because there's just a single derivative. The order is the highest derivative present in the equation. So All right. So first thing, the order is the highest. So order, highest derivative in the equation. So if we look carefully here at question 2, we look at this thing here. This thing is second order because we've got a second derivative term. All right. Now, my understanding is that you do not have to do much with second order differential equations. So you'll notice again with this question 2, the question is verify, and so we'd follow the same procedure. All right. So I'm like this assignment is actually really useful for going through and looking at the terms they're going to use. You're looking at the things that they're going to do, and we should be aware that your assignments or your tutorials are actually going to model the type of things you're going to be asked. Usually, the assignment things are a little bit more involved in that it's a little bit more thinking involved to get to the answer, and a little less about just being able to show your understanding of the topic. But they're a good guide for the type of things you might be asked. So, what's the next thing I'm asked? Find the general solution of the following differential equations. Do we know what general solution means? Okay, so this is 1 point. General solution. What general solution means is if there's some freedom in my equation. So since I haven't actually memorised or looked that carefully over all the notes, had to scan over them to make sure I knew what I was going to talk about, but didn't, because it's a bit of a request session, it's a whole semester's worth of stuff can be a bit tricky to revise. And so, may not be exactly how your lecturer said, but if I do this, if I look at these things, I quite often get some freedom. So if we look at, I'm going to quickly do the next one, where I've got differential equation dy on dx is equal to 1 on x. So I'm going to separate this out. I'm going to go dy. I'm going to put number 1 here, all right? 1 dy is equal to 1 on x dx. Now, this is because when we do this separation thing, the reason we split the dy and dx is so I can then sort of slip in an integral thing here. All right? So, do we remember about integrals? Yes. So we can quite comfortably say the integral of y, of 1 with respect to y. So technically, that's like the integral of y to the power 0 dy, which would be equal to y to the power 1. So I increase the power, divide by the new power. Ideally, I'd add a c. I'm going to call this c1. If I look at the integral of 1 on x dx, this is equal to the integral of x to the minus 1 dx. Now, if I did the same thing with this one, all right, if I increase the power by 1, I get 0. And that just feels wrong to me. All right? So that makes me go, does this fall into a special case? And there is a special case for integration. If I have 1 on x, the integral is ln of x. So this is going to be equal to ln. We often put the absolute value around x, and sometimes we don't. You should, is the answer. That you should put the absolute value around x to make it so that it's generally true. Okay? With this situation, we might come across, might be that for other considerations we are allowed to remove the absolute value, but for the purpose of doing general solution, we're going to work with just that information. Now, so what my equation here is saying, if I bring together this bit, I've said that this is y plus c1 is equal to ln of x plus c2. You will have noticed your lecturer has never done it that way. All right? Your lecturer will have told you that it's y is equal to ln of the absolute value of x plus some constant. And that's because we only ever we only ever put one of these constants in. All right, I've actually put them in, but if you imagine what we're going to do is we're going to put this C2 over this other C1 with C2, and they're going to combine to get me some other constant D. All right, and because I don't know what that constant is, there's no point in me sort of tracking a C1 and a C2 and doing all the bits to it. I might as well just go, it's some constant, and I will find that out later. So this is the general solution. And that's because it has this D, which is allowing us some freedom. There is an unknown in the equation. There's some freedom in what the solution actually is. So that's next part. So if I'm talking about general solution, the next thing I should talk about is particular solution. So I'm going to move on to, like I say, I'm loving this assignment because it's kind of should almost say to the person who wrote the assignment, they did a very good job, because they've gone through and said, they've sort of almost followed how they've given it to you in lectures. This is the type of thing, this is the question to do with it. This is the type of thing, these are the questions we're going to do with it, okay? So, next thing is particular solution. All right, so when we say particular solution, it is an exact solution to this thing. All right, and so if I take, I'm going to do another one, dy on dx is equal to e to the minus x on y squared, but they've given me one more piece of information. All right, I need to use something else. So before we saw there was something unknown in the equation. Now what we're doing is going, well, there should be more information for me to nail down exactly which function we want. So this is again separable. I'm going to write this as y squared dy is equal to e to the minus x dx, and we've separated it, so we put in the integral. So far so good. And so what we're going to do is we're going to go, okay, this one here gives me y cubed, so I increase the power, divide by the new power. Okay? Same thing. Now, do we know what the derivative of e to the x is? Because integration and differentiation are the opposite of it, so if I differentiate with respect to x, e to the x, I just get e to the x. If I differentiate with respect to x, e to k times x, chain rule says I get the function back and get the derivative of the whole outer function, and I've got to times by the derivative of the inner function, in this case that. And so the derivative of kx is just k. Now, integration is going back the other way. Sort of going, I'm taking this thing and I want to go back to this. All right? So because if I don't have the k here, I had to divide that whole equation through by k. In this case, minus 1. And so I'm going to have e to the minus x. I'm going to write it as divide by minus 1, because that's actually what's happening. And then I'm going to add my constant of integration. All right. So at this point in time, this is actually the general solution. All right. Possibly I'd go a little bit further and say y cubed is equal to minus 3e to the minus x plus c. You notice when I times through by 3, I didn't actually change the c. I just left it as c, because we're not bothering about tracking that. All right. There's no point in spending the time and energy following what's happening. So that's used. So far we've used this piece of information. We now need to use this piece of information so that we can get our solution. All right. So what this is saying is y is equal to minus 2 when x is equal to 0. So x equals 0, y is equal to minus 2. That's how we're supposed to interpret that information. So we've got have minus 2 to the power 3 is equal to minus 3 e to the minus 0 plus some constant. So far so good. E to the 0. Alright. 1. Yes, that's right. Well done. Minus 3 plus c is equal to minus 8. So therefore c is equal to, c is equal to minus 5. Alright. And so therefore my particular solution, y cubed is equal to minus 3x minus 3e to the minus x minus 5. Possibly I'd go one step further and go y is equal to the cube root of the minus 3e to the minus x minus 5. And I have to have that whole thing under the cube root. Okay? Do we got any questions thus far? Okay. What I'm going to do is I'm going to spend just a second. I might leave that up there for a second. So I'm going to spend just a second and see if I can't thumb through one of these exams. 2013 calculus, and see if I can't find an actual exam question to do for you that was asked in this sort of type. Does this type of thing. I think you're just having a pretty basic introduction to differential equations, and I'm not sure there is much more that you need to know, but I'm not sure that is a question. Sweet. Okay, so we'll finish this off with a question from the differential, from the actual exam. So I'll copy this out onto a separate piece of paper so that I can scan all these notes and put them up on the web with the lecture. So we've got question 6 here. Find the solution to the differential equation with initial condition. Okay, so we're going to ask ourselves, is it separable? We actually really only know how to deal with separable equations, so we're hoping it is. Then we're going to go through that process of going, well, we're going to find the general solution, we're going to find the particular solution, all right? So our differential equation is going to be dy on dx is equal to 4x divided by y. And our initial condition, y of 0 is equal to minus 1. So we call it an initial condition because we're talking about when x is equal to 0. All right? That's the bit that makes it an initial condition. So we're hoping this is separable so we can do the separation. And that's the first thing we're going to do. So we're going to times both sides by y to get myself y dy is equal to 4x dx. So we're going to slip in our integral sign here. Do the integration. So the integral of y, so hopefully we're up to the y to the power 1 goes to y to the power 2 divided by the new power is equal to 4x. So 4 times x to the power 1, which becomes x to the power 2 divided by 2, and then we have to add in some constant of integration. Now, ideally we want y by itself. So you notice last time I didn't do much. I left this as left it as function of y is equal to some function involving x. So timesing through by 2 is going to get me 4x squared plus our constant. All good. I could, at this point in time, go, well, y is equal to plus or minus square root of 4x squared plus c. Notice how I got that problem there? In fact, actually I'm going to do that. This particular one, we're going to work with this form, because sometimes we need to sort of do that look ahead and go, what could be a problem? If I'm taking the square root of y, I need to know whether my thing is a plus or a minus. And I'm noticing that my y is a negative. So I want to work with what exactly y is. So, when I'm coming down here, we got x is equal to 0, y is equal to minus 1. So general form. So my general solution, so now we're going to put in minus 1 is equal to plus or minus square root of 4 times 0 squared plus c. Okay, so first thing we notice is it can't be plus, can it? That won't get me the right function. Alright, they're going to do the thing you least expect, and in this case the thing you least expect is the minus. And so this is actually going to be minus square root of c. Alright, to make it, so the thing, what I get out of this, if you just ask what's the square root of something, the answer is always a positive number. If I'm asking, x squared is equal to 4, I can have x is equal to plus 2 or minus 2. And so because we've got a y squared is equal to something, we need to allow for that plus or minus. So in this case, we have to choose the minus to make sure we get minus 1. And so this is going to tell me that c is going to be equal to 1. All right, the thing under the square root has got to be 1. And so and that, I don't know what you think, but I look at that and go, actually that was 4 marks. 4 marks worth, sort of, what does it work out to be? Something like 6% of your exam. That didn't seem that hard, did it? Sweet. Okay, do we have any more questions about differential equations that we might see in the... Anyone? So as you saw, there was one question is worth about a 7, hang on, about 4 marks is what? It's a bit under a 7th. A bit under a 7th of the exam. That makes it nearly 10% of the exam. Hang on. Nearly 10% of that section. So 5% of the total exam. Alright, I'm going to stop this recording, start another one in a second, and talk about trapezoidal rule.